It's 2 a.m. You promise yourself you'll glance at one last space fact before bed. Instead, you're reading about astronomers finding exoplanets several times bigger than Jupiter. Suddenly, your mind jumps to a new question. What if one of those monsters slammed straight into another? And that's only the beginning. From planets that dwarf our own giants to cosmic structures spanning billions of light years, we'll see what happens when the largest things in the universe collide. We'll start small, well, planet-sized small, and end with crashes that reshape the cosmic web itself. First, what happens when two oversized gas giants meet? It's stranger than you'd think, when super exoplanets collide. Astronomers in 2025 no longer gasp at Jupiter's size. Once the heavyweight of our solar system, it looks modest compared to the discoveries pulled from nearby star fields. Among these finds are worlds so massive that astronomers debate whether they should even carry the title planet. Their dimensions edge into the realm of brown dwarfs, objects caught halfway between stars and planets. Place Jupiter beside one of these leviathans and the comparison makes it look more like a satellite than a peer. Their atmospheres stretch tens of thousands of kilometers deep, layers of hydrogen and helium piled into vast envelopes. These are the true planetary giants, and imagining them colliding is far from a simple rock-on-rock crash. When two of these swollen gas envelopes drift into each other's orbits, the first contact isn't solid ground, but cloud on cloud. Their outer layers, diffuse yet immense, meet like colossal balloons pressing together. As the atmospheres overlap, shock waves surge through the gas, compressing it until molecules split apart and electrons break free. In moments, entire regions ignite into glowing plasma, laced with brief flashes of electricity. To a telescope, that violence wouldn't look like a simple flare. It would register as intense bursts of infrared light, eruptions thrown out into space, along with huge jets of hydrogen and helium escaping from both planets. This upheaval would shred nearby moons or fling them away entirely. But the deeper catastrophe comes when the hidden cores are dragged together. Beneath the swirling gases, each planet shelters a compressed center of rock, metals, and exotic high-pressure materials. Gravity forces these dense cores into a collision at relative velocities of many kilometers per second, depending on their orbital dynamics. The meeting is brutal, more like smashing two mountains of compressed metal together than anything remotely gradual. The impact liberates fierce amounts of energy, released as heat, causing violent turbulence throughout the merged object. Once the dust, figuratively speaking, settles, the result is a new world. If the combined body tips the scales below a certain threshold, it remains classified as a planet, though a swollen and unstable one. But if the total climbs above about 13 Jupiter masses, the approximate deuterium fusion boundary, the object crosses a line. The internal pressure now becomes strong enough to ignite deuterium fusion. The end product is not a star in the familiar sense, because it cannot sustain hydrogen fusion like the Sun, but a brown dwarf, an object glowing faintly in infrared light, appearing star-like to observatories. That glow becomes a signature for astronomers. Ordinary planets don't produce it, but a newborn brown dwarf radiates like an ember against the cold background, betraying its violent origin. Many of the faint points detected in young star systems are thought to be precisely this: giant planets that crashed together in their early youth, fused into something between a world and a star. And thanks to direct imaging campaigns, telescopes like JWST are now sensitive enough to pick out not just brown dwarfs, but glowing companions as small as Saturn. These observations make the collision scenario more tangible, not just speculation, but something that leaves traces modern instruments can actually catch. The aftermath extends outward into the planetary system. One impact takes hours to days for the initial atmospheric storm to stabilize, centuries for the fused body to cool into relative equilibrium, and millions of years for the rest of the system to reorganize around the altered gravity. Moons may coalesce from leftover debris, while smaller planets get nudged out of their stable tracks. A single smash between gas giants doesn't just create a hybrid planet, it can rewrite orbital maps across a whole solar system. Observations of puffed-up hot Jupiters may already hint at this process. These worlds orbit close to their stars yet appear larger than physics predicts. A likely explanation is that they suffered massive impacts in the past, leaving their interiors overheated and distended. Over long timescales, they shrink back toward equilibrium, but for millions of years they remain bloated relics of their collisions. Catch one of these impact events mid-process, and the swelling would be accompanied by glowing plasma bursts, rapid heating, and striking radiance visible far away. All of this underscores how thin the border is between planet and star. Super exoplanets already occupy a fragile category, balancing near the mass boundary where nuclear fusion awakens. A single merger can provide the tipping point, transforming two planets that never quite earned stardom into one that glows like a faint star, though never fully stable. That glow is more than spectacle. It is a cosmic marker of destruction, the quiet ember left behind when massive worlds refuse to share their space. So the next time you see a brown dwarf listed in a star catalog, remember it may carry the history of a colossal impact, two titanic planets combined into one luminous remnant. Two superjupiters don't just add up to a larger ball of gas, they can reshape the architecture of an entire planetary system. And if planetary collisions already reach such extremes, imagine what happens when even larger players in the universe decide to crash together, colliding with a Titan star. By 2025, astronomers have measured some of the universe's most extreme stars, red hypergiants. VY Canis Majoris and Stephenson 2-18 are prime examples, swollen, unstable giants nearing the end of their short lives. Their outer layers are so extended that, if one were placed where our Sun is, its photosphere could stretch out beyond Jupiter's orbit and in some estimates reach into the realm of the outer planets. These stars don't shine with the concentrated intensity of smaller, hotter stars. Instead, they spread their energy thinly over an immense surface. Imagine a single luminous sphere, so vast it could engulf the inner solar system in glowing hydrogen gas. And now, imagine a second of equal size drifting too close. When these enormous atmospheres first touch, the moment is surprisingly quiet. Their outer envelopes are mostly diffuse gas, so the overlap looks more like immense fog banks blending in space than a fiery smash. Pockets of hydrogen and helium mix together, creating slow, billowing flows. To the eye from afar, it would seem almost gentle, like sheer size has stripped away the violence. But that appearance masks the danger, because deep inside these stars their cores are already unstable, fused into layers of heavier and heavier elements. The risk comes not from the surface mingling, but from what happens when the inner fusion engines cannot withstand the added strain of combined mass. The central regions of hypergiants are precarious, gravity pressing inward, radiation pushing outward, fusion occurring in shells of progressively heavier nuclei. Once two of these cores begin to overlap or interact, they shove the system past a limit. Instead of stabilizing, the star's heart races toward collapse. Fusion reactions ignite faster, the pressure mounts, and eventually the balance breaks. When two unstable giants merge in this way, the enlarged core cannot hold itself up. Within a short time, the core gives in. Gravity wins completely. That collapse is sudden on stellar timescales. The inner core contracts in seconds. Outer layers, which once drifted gently, now lose all support and fall inward, accelerating until temperatures and densities skyrocket. This runaway collapse ignites explosive fusion, carbon, oxygen, silicon, flaring in layers as the star tears itself apart. The result is a core collapse supernova. The star's interior becomes an uncontainable machine, releasing energy outward in the form of neutrinos and shock fronts that rip through the surrounding gas. To an outside observer, it is not subtle. The explosion cuts across the galaxy like a lighthouse flare, easily outshining billions of ordinary stars. The aftermath depends on what survives at the center. If the mass of the collapsed core is modest enough, it forms a neutron star, a compact object no bigger than a city, so dense that a teaspoon of its matter would outweigh mountains. But if the merged hypergiant exceeds the neutron star threshold, then even neutron pressure fails and a black hole forms. This black hole would carry away the legacy of two colossal stars, dense and invisible except for the energy released as matter spirals into it. Beyond their spectacle, collisions like these perform essential cosmic work. They forge heavy elements. Iron, gold, uranium, atoms too heavy to form under ordinary stellar fusion, are created within the furnace of the explosion. then hurled into surrounding space by the blast. These atoms seed the galaxy over time, becoming part of new stars, planets, and the raw materials for future life. Every ring of gold or circuit board on Earth carries atoms born in ancient detonations of massive stars. Without these collisions, the universe would lack many of the elements on which complex chemistry depends. From Earth, we would see consequences both immediate and long-lasting. If such a merger occurred in a nearby galaxy, its brightness could rival all other stars in that system combined, lasting for weeks or months before fading. The expanding remnants, filaments of glowing gas shaped by shock waves, would trace ghostly outlines across thousands of light years, and telescopes could track them for millennia, measuring how they enrich interstellar space with fresh material. In dense stellar clusters, the effects ripple outward. A supernova blast born of colliding hypergiants could sterilize entire regions, stripping nearby planets of their atmospheres and ending life before it begins. Yet the debris also enriches those regions with critical elements, increasing the chances that future star systems form planets rich in carbon, oxygen, and metals. The trade-off is stark: destruction of existing environments in exchange for improved conditions in worlds yet to come. Not all hypergiant encounters look like instant collisions. Sometimes two giants meet and form a close binary system. In this arrangement, one star can siphon matter from the other, drawing away vast streams of gas. Over time, the more massive star swells far beyond its already enormous size and tips into collapse. Here, the collision is stretched over thousands of years, slow cannibalism rather than a swift merger, but the end state is the same. Once enough mass comes together, the unstable cores can't hold equilibrium, collapse follows, and the region is lit by one of the brightest explosions in the universe. The key lesson is fragility. When hypergiants swell to such immense sizes, it doesn't signal strength, it signals decay. Their vast dimensions exist only because their interiors are running out of sustainable fuel and pressure is losing ground against gravity. Place two such unstable stars together and their decline accelerates. What seems like grandeur is really a warning sign, and the final act is violent collapse on a galactic scale. Astronomers scanning young star-forming regions may one day witness such a merger directly. The chances are slim, since hypergiants live only a few million years and require precise conditions to collide. But if caught, it would show the cycle of cosmic recycling in real time. Titanic stars expiring in a single flash, dispersing the building blocks for unknown futures. And this was the fate of colliding giant stars. But what happens when the wreckage they leave behind, the dense corpses of dead stars, crashes together instead? That was the calm part. The next collisions are far smaller, far denser, and far more explosive. The neutron star collision showdown. Everyone's heard about black holes crashing together, but neutron star mergers remain strangely underappreciated, which is odd because they're the rare kind of collision that is both catastrophically violent and dazzlingly luminous at once. A neutron star is what remains when a massive star dies in a supernova but stops short of collapsing into a black hole. It's only about 20 kilometers across, roughly the size of a city, yet it contains more mass than our sun. A single sugar cube of this matter would outweigh every building in a major city. Now imagine two of these ultra-dense remnants locked on a collision course, drawn together by gravitation itself. The typical setup isn't a random crash, but a long spiral. Two neutron stars form a binary system and circle each other for millions of years, slowly radiating away their orbital energy in gravitational waves. Every pass eats away at their separation, drawing them tighter until the orbit shrinks drastically. They eventually whirl around one another hundreds of times per second, moving at a significant fraction of light speed. As they spin, the ripples they send through space-time intensify. Not sound, not light, but oscillations of space-time itself. Observatories tuned to that frequency, like LIGO and Virgo, have recorded the chirp of such spirals, the most famous being GW 170817 in 2017. That event was a turning point, the first time astronomers caught both the gravitational wave signal and a matching electromagnetic afterglow. confirming that neutron star collisions power Kilonovae and synthesize heavy, hard-process elements such as gold and platinum. What makes these collisions distinct is that neutron stars have no soft outer layers. They're essentially exposed cores of degenerate matter with almost no atmosphere to cushion them. So when they meet, it's bare surface against surface, an unforgiving slam. The first contact shreds crustal material and flings it outward at a fraction of the speed of light. That material is saturated with neutrons, and as it escapes, it decompresses and undergoes rapid neutron capture, creating new atomic nuclei. To telescopes, this eruption shows up as a kilonova, an expanding cloud that glows brilliantly across multiple wavelengths before fading in days to weeks. In the case of GW 70817, dozens of observatories around the world watched precisely that fading curve, a rainbow-like spectrum proving where elements heavier than iron truly come from. The violence doesn't stop with the ejected matter. Along their magnetic poles, neutron stars can channel jets that puncture the debris and release short bursts of gamma radiation. These flashes, lasting mere seconds, briefly rival the total output of the entire universe, as long as you happen to be in the narrow line of fire. If a jet were pointed at Earth from close by, the outcome could be catastrophic for the atmosphere. Fortunately, such alignments are rare. In most gamma-ray bursts we detect hail from galaxies millions or billions of light-years away. Back at the core, nature makes a decisive choice. The merged object may momentarily form a hypermassive neutron star, stabilized for seconds by rapid rotation and thermal pressure. But if its mass is too great, gravity overwhelms those supports and forces collapse into a black hole. Both outcomes release staggering energy, but most of it escapes in forms invisible to us: gravitational waves, neutrinos, and radiation across the spectrum. The measured power is immense. In GW 17817, detectors caught signals equivalent to one of the brightest astrophysical explosions ever observed, rivaling any supernova and surpassing most other cosmic outbursts. This output wasn't just light, but a combined flood of messengers, space-time ripples, neutrino flux, and bright optical afterglows. For astronomers, these mergers aren't only spectacular, they're uniquely informative. They offer the one environment in which matter composed almost entirely of neutrons can be probed, something laboratory experiments on Earth cannot simulate at such densities. Each afterglow provides data about how dense matter behaves, how magnetic fields evolve under extreme compression, and how our process nucleosynthesis unfolds. Today, with sophisticated numerical simulations and breakthroughs in machine learning, astronomers can model these high-density mergers in advance. That allows telescopes to pivot quickly when gravitational wave detectors raise an alert, catching the bright, short-lived light before it fades. The most striking consequence of neutron star collisions is their role in the periodic table. The heavy elements essential to planets, technology, and even life, the gold in electronics, the platinum in catalysts, the uranium deep in Earth's crust, emerge from these cosmic foundries. With each merger, galaxies gain fresh supplies of our process material, spreading through interstellar dust, joining nebulae, and ultimately condensing into new star systems. Our solar system itself carries chemical fingerprints of multiple ancient Kilonovae that seeded the gas and dust from which Earth formed. Without such collisions, Earth would lack the very ingredients that shape geology and biology. On human timescales, though, the direct risks are minimal. A neutron star collision within a few dozen light-years could potentially impact Earth's biosphere with intense gamma radiation, but such events are vanishingly unlikely. The nearest observed mergers have all been millions of light-years away, bright enough for us to detect with our current instruments, but harmless at that distance. At most, a kilonova glimpsed from relatively close range in the Milky Way would light up the night sky for weeks. Still, by far the more significant danger is elemental. Those same events long ago seeded the very atoms we carry. Seen in this light, neutron star collisions are less about endings than beginnings. They are recycling systems, taking stellar corpses and smashing them into factories of atoms that shape future generations of planets and ecosystems. They compress violence and creation into one event, tearing apart degenerate cores while simultaneously expanding the palette of elements available to the cosmos. Every observation enriches not only our catalogs, but our grasp of fundamental physics, how matter behaves when crushed beyond atomic structure, how space-time records these impacts as ripples, and how bright transient fireworks echo across galaxies. The image is remarkable. Two dense spheres, each the size of a city but packing more than a solar mass, circling each other at breakneck speed. Their final spiral churns space-time itself, and then, in one instant of collision, reality reorganizes. Matter ejects, elements are born, and a new compact remnant emerges. In the days that follow, the flare of a kilonova sizzles through telescopes, then fades into memory, leaving behind only heavier atoms drifting outward. Eventually, those atoms seed new star systems, new planets, perhaps even life. Neutron-star collisions stand as both the loudest nuclear forges in the cosmos and precise probes of exotic matter. They remind us that the richness of the universe, its metals, its chemistry, its complexity, owes as much to destruction as to creation. For that reason, they deserve not just attention, but prominence. And while these star corps smash-ups are extraordinary, an even more massive class of collisions lies in wait. What happens when objects millions to billions of times heavier than neutron stars begin their own long spirals? The stage shifts from stellar remnants to the heaviest engines the universe has ever built, the supermassive black hole ballet. The scale changes again here, moving far beyond dead stars and compact remnants. Now the spotlight falls on the largest black holes, the ones sitting at the centers of massive galaxies. This is the realm of the supermassive black hole ballet. These black holes are so big that one of them can outweigh tens of billions of suns, reshaping entire galaxies around their presence. Recent studies have measured a few candidates in the range of 30 to possibly 100 billion solar masses, including ultramassive objects in galaxy clusters like Phoenix A. None stand alone as a singular champion, but the pattern is clear. Black holes can grow to extraordinary extremes, and they do it at the cores of the largest galaxies known. The unsettling, yet fascinating question that follows is what happens when two of these colossi are set on a collision course. The first thing to understand is that supermassive black holes don't rush headlong toward impact. Their movements are governed by vast amounts of orbital energy, and shedding that energy takes extraordinary time. When two galaxies merge, their central black holes drift closer together, drawn into mutual orbits by gravitational attraction. But they don't collide in years or lifetimes. These spirals take billions of years to close. Like whirlpools circling in an unending ocean, they slowly drain energy away into their surroundings until only gravitational waves can carry their last momentum. It is only in the final stage of the merger, after epochs of circling, that their horizons finally touch. During those long ages, each orbit sends out ripples in space-time. These are gravitational waves, flecks of curvature spreading outward at the speed of light. They're faint on human scales. Distances change by less than the width of a proton when waves pass through Earth. But across cosmic distances, the accumulated energy is staggering. Different detectors are tuned for different mass scales. Instruments like LIGO and Virgo pick up waves from stellar mass black hole pairs, while pulsar timing arrays and, eventually, giant space-based observatories will be needed to catch the slow, deep signals from supermassive mergers. Each technique captures a different register of spacetime's long symphony. Seen from afar, the galaxy hosting such a system does not show reckless fireworks. Instead, the cores appear as twin bright nuclei surrounded by turbulent accretion disks. The gas and dust heated by their pull radiates across X-ray and ultraviolet bands, lighting up the center. Occasionally, jets erupt outward, magnetically accelerated streams of matter pointing for thousands of light years. These signatures can reach us more directly than gravitational waves, letting astronomers spot merging black holes before their horizons have blended. Observations already show galaxies with dual active nuclei, clear evidence that these systems exist and that black hole pairs are spiraling quietly toward the final act. To put the scale in sharper relief, remember that a stellar mass black hole might span only a few kilometers across, When you climb to something measured in tens of billions of solar masses, the event horizon can stretch wider than our solar system itself. Light near such horizons behaves strangely, curved into distorted paths, doubled or lensed into arcs as it tries to escape. With two of these behemoths side by side, the warped region becomes even more intricate. This bending isn't something you'd notice standing nearby. It requires careful measurement with advanced instruments. But the telescopes, the distorted images tell a clear story of enormous objects circling each other. As the spiral progresses across countless millennia, the frequency of gravitational radiation increases. The black holes move faster, losing energy more quickly until the final plunge begins. That last approach happens surprisingly fast compared to the long buildup. Mere hours or days may see the horizons meet. When they touch, the two voids merge seamlessly into one larger singularity, their boundaries reshaping instantly like drops of liquid merging in water. The process releases mass equivalent to millions of suns, carried away not in visible light but as gravitational energy. In terms of raw physics, this is among the greatest outbursts the universe allows, silent and invisible to human senses, yet capable of being detected across intergalactic distances by the right instruments. Afterward, the remnant is more massive than either parent but slightly lighter than their simple sum, thanks to the energy carried away. Its spin and orientation depend on the geometry of the merger. If alignment was neat, the result spins, rapidly driving strong accretion flows and powerful outflows. If the collision was skewed, some rotational energy is lost, leaving a slower spinning hole. These details matter because they set how future activity at a galaxy's heart unfolds. Jets, accretion disks, and entire galactic environments change depending on what kind of central engine emerges. Astronomers have ample evidence that such growth happens repeatedly. Many large galaxies show telltale signs of dual cores and ultramassive candidates inside the largest clusters. This points to a history of mergers, with each event growing the central black hole larger than before. Over cosmic time, these repeated dances may explain how some galaxies ended up with monsters nearing 100 billion solar masses. Observations in 2025 already hint that candidates scattered across fossil groups and massive ellipticals, reinforcing the idea that collisions drive the highest end of black hole growth. From our perspective, the release of gravitational energy in these mergers is unthinkably large, yet invisible without instruments attuned to space-time itself. Our eyes see galaxies and starlight and feel confident we're witnessing the universe's dominant output. But the truth is different. Gravitational waves from black hole mergers carry more combined energy than the light of all the stars we can observe, just hidden from our senses. For now, gravitational wave astronomy is still young, but by listening with better detectors, humanity is learning to hear these colossal events, reconstructing collisions that happened billions of years ago. The essential point is that supermassive black hole collisions are not violent spectacles rushing past, but vast, slow-motion tsunamis in spacetime. The bright light shows us their setting, but the true energy moves through silent ripples. Galaxies hold these dances at their very centers, their timelines too immense for civilizations to witness directly, though their echoes travel the cosmos for anyone prepared to detect them. So supermassive black hole mergers are slow-motion cosmic tsunamis, quiet to our senses but deafening in gravitational energy. Next, what happens when entire galaxies collide? The galaxy smash, giant spirals versus cannibals. UGC 2885, nicknamed the Godzilla Galaxy, earns that title because it's one of the largest known spiral galaxies, a sprawling disk of stars and gas that makes our Milky Way look small. On the opposite end of galactic form are the vast ellipticals that dominate the centers of clusters. These are the cannibals of the cosmos, galaxies that have already consumed smaller neighbors and digested them into smooth, featureless spheres of stars. It sets up a remarkable contrast, a grand spiral with structure and order, facing a bloated elliptical built on centuries of mergers. When such systems converge, the scale is staggering. Billions of stars, millions of nebulae, central black holes, and entire dark matter halos all participate in one drawn-out collision. The merger follows a predictable sequence of stages. First come the halos. Both galaxies are wrapped in immense, invisible clouds of dark matter that extend far beyond their visible disks. These halos meet well before the bright disks overlap. Their gravitational tug alters stellar orbits, redistributes angular momentum, and pulls at the outer edges of the galaxies. The first signatures are tidal tails, streams of stars stretched into ribbons that extend tens of thousands of light years, long before the cores actually touch. To telescopes, these tails look like luminous threads unraveling from the edges of galaxies still far apart. After the halos destabilize things, gas takes center stage. Stars are usually so far apart they pass by unharmed, but interstellar gas clouds cannot avoid contact. When cold hydrogen clouds collide, they compress and heat, triggering bursts of star formation. The scale of this activity is far beyond ordinary galactic rhythms. Known as starburst regions, these events can ignite thousands of stars across whole arms of the galaxy in a relatively short time. From a distance, the system brightens dramatically, dotted with glowing nebulae and flashes of supernovae from the most massive stars born in the frenzy. Astronomers have observed these events in merging systems, showing that collisions can briefly transform galaxies into the brightest star-forming regions in the sky. Such powerful starbursts also exhaust reserves of gas, setting the stage for the galaxy's transformation into an elliptical over time. The final stage centers on black holes. Each galaxy carries one at its core, ranging from millions to billions of solar masses. During the early phases of a merger, both nuclei may still be visible as distinct, active centers surrounded by disks of hot gas. Observers call this a dual-core system, and their accretion flows amid X-rays and high-energy radiation that shine across galaxies. Over millions of years, dynamical friction brings the two black holes closer until they orbit one another, spiraling slowly inward. They may continue this dance for eons before their horizons eventually meet in a merger of supermassive proportions. That final step, as described earlier, produces gravitational waves powerful enough to ripple across intergalactic space, leaving their mark long after the bright signatures fade. While these major steps unfold, the stars of both galaxies find their quiet stability shredded. Many are hurled out into intergalactic space, becoming rogue wanderers no longer bound to a single home. Others are caught on destabilized paths that swing close to the central black hole, where some may be torn apart in tidal disruption events. The result of this reshuffling is an increasingly chaotic stellar distribution, a visible distortion recognizable even from millions of light years away. Telescopes focused on these mergers record the curved tails, starburst knots, and brightened unstable cores that sketch out the process in real time. Galaxies rarely collide in a single clean pass. More often, they loop together through a series of encounters. The first approach warps their arms and ejects long streams of gas and stars. Then, after drifting apart for a time, gravity drags them back. Each pass strips more structure and transfers more energy into tidal features and starbursts. This cycle can repeat several times across hundreds of millions of years before the galaxies finally coalesce into one. It is less a single crunch than a long sequence of gravitational exchanges that erase the original spiral or elliptical features until only a blended system remains. Ultimately, the merger produces a super-elliptical galaxy. Spiral arms fade into uniformity, gas reserves decline after intense starbursts, and the system settles into a smooth spheroidal body dominated by its central black hole. To outside observers, it appears as a diffuse glow, without distinctive arms or dust lanes, the legacy of past violence hidden beneath a deceptively calm outline. This is why so many elliptical galaxies are thought to be merger remnants, the product of repeated collisions and the restructuring of once ordered systems. The energy that drives this transformation doesn't vanish. Each burst of star formation radiates strongly across the spectrum. The brightest young stars die quickly in supernovae, seeding their surroundings with heavy elements. Heated gas glows in X-rays, a signature often used by astronomers to identify active mergers in progress. When combined with the visible structures of tidal tails, these high-energy signals mark galaxies mid-collision, allowing researchers to estimate how far along the process has advanced. Nearby companions rarely escape untouched. Smaller satellite galaxies orbiting the main pair can be stripped of stars or torn apart entirely. Their remnants often stretch into faint stellar streams observed crossing intergalactic distances, direct evidence of smaller galaxies absorbed during larger encounters. These features show that mergers affect not just the titans at the center, but also the dwarfs caught in their gravitational reach. UGC 2885 stands as one of the largest spirals we know, and an encounter with a comparable elliptical would be catastrophic for its structure. Over millions of years, its distinct arms and dust-rich lanes would blur into the wider glow of an elliptical, unique character traded for mass and permanence. This outcome illustrates the long-term fate of many spirals. Their existence is fragile against the inevitability of collisions in dense environments. Growth comes at the cost of identity, with only the smooth brightness of an elliptical left behind. These transformations are not fast by human standards, but they rewrite entire galactic architectures. They replenish heavier elements for future star systems, redistribute stars across intergalactic space, and fuel the growth of central black holes. Each collision feeds into the larger process of structure formation, building galaxies larger, rounder, and heavier than their precursors. From our vantage point, we can trace these events through tidal streams, starburst activity, X-ray gas, and eventually, the quiet glow of ellipticals. They are some of the most dramatic reorganizations in the visible universe. And yet, even these titanic duels are just one level of cosmic hierarchy. Galaxies rarely exist in isolation. They group together in the hundreds or thousands, bound by vast halos of dark matter. When such groups clash, the violence and spectacle far exceed even the largest galaxy merger. When galaxy clusters collide, the Phoenix Cluster and El Gordo are not just catalog names. They represent some of the most massive galaxy clusters astronomers have measured. Each one binds together hundreds of galaxies, reservoirs of superheated gas, trillions of stars, and vast halos of dark matter. Their total masses sit on the order of 10 to the power of 15 solar masses, about a quadrillion suns held in one gravitational field. Thanks to high-resolution images and data available by 2025, astronomers can now examine their motions, temperatures, and shock fronts in remarkable detail. And with that detail comes a direct question. What happens when two whole clusters of this size collide? To answer, start with the essentials. The first interactions are not between stars or black holes, but between the diffuse superheated gas clouds that fill the space between cluster galaxies. This intracluster medium glows in X-rays because it reaches temperatures of tens of millions of degrees. When two clusters interpenetrate, these gas reservoirs smash together head-on. The result is shock heating, with luminous fronts spanning millions of light-years. Observatories tuned to X-rays capture these features clearly, rippling arcs and waves that trace the violence across intergalactic scales. In many cases, the temperatures exceed what is found in stellar cores, meaning the cluster's halos briefly contain some of the hottest matter in the universe. The second effect concerns dark matter. Unlike gas, dark matter doesn't collide directly. It passes through, interacting only through gravity. This distinction produces one of the clearest observations supporting the existence of dark matter itself. In systems like the famous bullet cluster, astronomers have seen ordinary gas slowed by collision while galaxies and dark matter halos continued forward almost undisturbed. Gravitational lensing studies reveal the offset: glowing X-ray gas on one side, galaxies on another, and the bulk of the mass, dark matter, mapped separately by how it bends background starlight. Cluster mergers replicate this pattern on even larger scales, showing ordinary matter and dark matter diverging under different rules. Third, there's the behavior of the galaxies themselves. While galaxies don't strike each other directly, interstellar distances make those encounters vanishingly rare. The gravitational tides from two colliding clusters change their paths dramatically. Individual galaxies can be pulled into slingshot orbits that fling them clear of the new cluster, sending them off as solitary wanderers in intergalactic space. Others are slowed and redirected into dense cores, where their central black holes may eventually sink and merge into the cluster center. Observers have found examples of galaxies trailing alone, cut loose from any cluster environment, evidence that these gravitational throwouts are not rare. The collective outcome is one of the most energetic events the universe permits. When gas shocks propagate through merging clusters, they radiate X-rays powerful enough to rival the combined emission of many galaxies. At the same time, electrons spiral at nearly light speed in the turbulence of magnetic fields, producing vast arcs of radio emission called relics. These radio structures stretch across megaparsecs, ghostly outlines of the shocks racing outward. Combined with lensing data, they let researchers reconstruct the full story of a collision, where the dark matter drifted, where the gas slowed, and where galaxies were hurled into new orbits. Supermassive black holes within the galaxies add still more complexity. As their host galaxies are jolted by tidal forces, the black holes shift trajectories too. Some will eventually pair up in the cluster's core and begin the long spiral toward merger, generating deep gravitational waves across the slowest frequencies detectable only through pulsar timing arrays. Others may be set adrift, expelled as their parent galaxies are stripped apart. A black hole weighing millions or billions of solar masses wandering the intergalactic medium is one of the byproducts of this chaotic reshuffling, unlikely to be seen directly, but suggested by the trails they might leave through surrounding gas. The timescales are immense. A galaxy merger may unfold over a few billion years, but cluster mergers can stretch even longer. Within them, dozens of subcollisions take place. Groups of galaxies merge within the larger system, creating their own shocks and slingshots, each adding new ripples to the structure. Over time, all these smaller interactions combine into one vast halo tens of millions of light-years across. What emerges at the end is a swollen cluster, hotter, denser, and dominated by a deep dark matter potential, well sculpted by the long history of collisions. Star formation inside these mergers follows a pattern too. At first, the shock compression of gas can ignite starbursts in individual galaxies that still have fuel to burn. But as more gas is stripped, heated, or dispersed into the cluster medium, star formation slows. The aftermath is a giant entity with relatively little cold gas left. Its galaxies become redder and older, dominated by aging stellar populations and fewer bright blue young stars. In this respect, cluster mergers may help explain why massive clusters today often appear as red and dead assemblies of galaxies rather than vigorous star factories. The number counts push the mind to its limits. A galaxy may host hundreds of billions of stars, and a cluster merges hundreds of such galaxies. When two clusters like Phoenix and El Gordo come together, the physical ingredients involve tens of trillions of stars, thousands of black holes, and volumes of plasma larger than any single galaxy. Yet the true clash is not about stars striking stars. It's about gravitational rearrangements and shock fronts that reshape matter on larger scales than any stellar system could manage. Astronomers trace these events through three primary signals: extended X-ray maps that capture hot gas and shock fronts, radio relics that chart accelerated particles at collision boundaries, and lensing maps that reveal the hidden paths of dark matter. Only by combining these observations does the full picture emerge, showing how differently each ingredient, gas, galaxies, and dark matter, responds when the largest cosmic structures collide. Seen this way, cluster collisions are not just dramatic. They are laboratories. They reveal the physics of high-energy plasmas. They separate visible and invisible forms of matter, and they reshape the long-term evolution of galaxies trapped within them. Their scale and duration resist our ordinary sense of time, but the snapshots caught by X-ray telescopes, radio arrays, and lensing reconstructions capture them in action. The lesson of these collisions is clear. The largest structures in the universe are not static. Their histories are written in shock fronts and distorted light, evidence that gravity continues to reorganize matter on scales of millions of light years, and the most intriguing part may be what these giants tell us about the hidden mass moving within them. Because if gas lights up and galaxies shift, yet the bulk of matter keeps sailing on almost untouched, then the real story is written in something we cannot see. That in turn leads to the darker question: what happens when the unseen structures themselves collide, leaving only gravity as their footprint? The dark matter clash. If galaxies are islands of light, then dark matter is the invisible terrain their foundations rest on. Astronomers estimate that more than 4/5 of every galaxy's mass belongs to dark matter rather than the luminous stars, planets, or gas we can see. Every spiral arm, every stellar orbit, and every drifting cloud in interstellar space is ultimately shaped by these vast, unseen halos. And here lies the puzzle. When such halos, the largest mass component of galaxies and clusters, collide with one another, what really happens? The single clearest lesson so far comes from cluster collisions like the bullet cluster. In those observations, ordinary matter and dark matter behave very differently. While the hot gas clouds crash into one another, shock, and slow down, the dark matter halos largely pass through, interacting only by gravity. That separation creates an extraordinary diagnostic. X-ray maps show gas lagging behind, while gravitational lensing maps show the bulk of the mass, dark matter, streaming through almost unaffected. The effect is subtle in appearance but profound in influence. Stars keep orbiting, galaxies are nudged into new positions, and over billions of years, dark matter's gravity dictates how entire clusters of galaxies rearrange. The challenge is that we cannot see the halos directly. They give off no light and absorb nothing. The method astronomers use to uncover their presence is gravitational lensing. Light from more distant galaxies is warped as it travels through the distorted space-time produced by dark matter. By measuring the arcs and subtle shifts in thousands of background galaxies, researchers can reconstruct where the hidden mass lies. When two halos collide, these lensing maps often reveal striking offsets between visible matter and dark matter, offering some of the most persuasive evidence that the invisible component has a real physical presence independent of ordinary gas and stars. This informs how we visualize a collision. Unlike clouds of gas, dark halos don't slam into one another and burst into fire. What happens instead is that their enormous gravitational fields overlap, tugging and tilting entire galaxies into new directions. A merger of giant halos becomes a gravitational resculpting of space itself. Galaxies are nudged into orbits they would never otherwise cross, sometimes flung far from the centers of clusters, sometimes dragged deeper inward. To picture it, imagine a board where galaxies are the pieces, but the rules of how they move shift when the invisible weight of two halos passes through each other. Does dark matter always pass like a ghost? Not necessarily. Some theoretical models propose that dark matter might interact weakly with itself. If so, then two colliding halos could experience subtle drags or trace amounts of resistance. These effects would be vanishingly small compared to the violent shattering of gas, but spread over cosmic time, even tiny additional forces could smooth halo cores or alter density distributions. Detecting such signals is now one of the active frontiers of research. If measurements ever show clear self-interactions, it would reshape physics at the most fundamental level, while also explaining why galaxies have the structures we observe today. These mergers do more than shift individual galaxies. They shape the largest patterns we see in the cosmos. The great filaments, sheets, and walls of galaxies crossing billions of light years are held together not by stars, but by the overlapping gravity of dark matter halos. Collisions between those halos sculpt knots and crosspoints in the cosmic web, creating the crowded regions where clusters develop and the underdense voids between them. Without the repetitive motions of halos merging and passing through one another, the universe would lack its striking sponge-like structure. From our perspective, every map of galaxy distribution is essentially a chart of previous dark matter collisions. Concrete consequences also flow down to smaller scales. Within halos, satellite galaxies, the dwarfs orbiting larger hosts like the Milky Way, record scars of past encounters. Mergers between halos alter the orbital tracks of these dwarfs, tilt their alignments, and sometimes scatter them entirely. Streams of stars winding around our own galaxy are relics of such events, following trails left by smaller halos captured and consumed. Even though the dark matter itself is unseen, its long gravitational reach imprints itself on the visible star maps astronomers now trace in exquisite detail. The Milky Way's entire history illustrates this principle. Debris from the Sagittarius dwarf galaxy, long stripped into thin rivers of stars, arcs around our sky. What tore it apart was not just tidal forces from visible stars, but the underlying framework of overlapping dark matter halos. These past interactions have shifted the structure of our disk and continue to influence stellar motions today. In effect, the solar system resides inside a galaxy whose present form has been sculpted by countless invisible collisions stretching back billions of years. On even larger temporal scales, halo mergers might also be recorded in low-frequency gravitational signals. While detectors like LIGO and Virgo capture the high-pitched chirps from stellar mass collisions, dark matter movements operate on wavelengths millions of years long. Future observatories and pulsar timing networks may reveal a continual low-hum sewn into spacetime itself, a gravitational record of halos colliding across the history of the universe. These waves would not resemble short bursts but long, drawn-out oscillations, matching the leisurely pace of massive halos sliding through each other. It remains important not to confuse passing through with doing nothing. Dark matter interacts dominantly through gravity, and that interaction is anything but minor. Its pull steers galaxies, stabilizes clusters, builds filaments, and limits how stars are distributed. Even when halos overlap quietly, their gravitational reach is active, slow-motion sculpting that permanently changes the orbits of galaxies, the shapes of clusters, and the arrangement of cosmic structure on every scale. In cluster collisions where ordinary gas lights up in X-rays, what astronomers really examine is how the luminous matter lags behind the dark matter. That separation is not just observational detail. It is the heart of the case for dark matter's existence. Without collisions to reveal it, we might still be left debating whether unseen matter was real or an accounting trick. Instead, halo impacts give concrete evidence. The invisible is out there, and it carries most of the universe's mass. So while the spectacle of dark matter clashing may lack fireworks of light, the consequences are vast. Stars remain intact, gas heats and erupts, but over and above these, entire galaxies are nudged into different lives, and cosmic scaffolding rearranges itself. Quietly, invisibly, halos set the rules, fling galaxies outward, and concentrate clusters inward. Halo collisions silently restructure orbits, fling galaxies, and over time sculpt the cosmic web. So dark matter collisions are quiet but decisive. And beyond such halos lies an even greater framework, the interwoven strands that bind the universe's structure end to end. Colliding cosmic filaments. Picture the universe as a three-dimensional web, a structure whose strands stretch for billions of light years. Along those strands sit galaxies like beads on a thread, forming vast highways of matter. Astronomers call these filaments, and they make up the skeleton of the cosmic web. Recent JWST results and wide-field surveys like Cosmos Web have mapped filaments out to earlier cosmic times, confirming that this lattice structure defines how galaxies assemble. The true question, though, is this: what happens when two of these filaments don't stay apart but drift until they intersect? The physics here looks nothing like smaller-scale impacts. When planets collide, the outcome is fireballs. When neutron stars merge, they spray heavy elements into space. But filaments don't behave explosively. Instead, their motion plays out through quiet distortions of gravity. Whole clusters of galaxies are passengers tied to these megastructures, shifting course as the underlying highways twist. From our perspective, a filament collision is the slow reorganization of hundreds of millions of light years, not a burst of light. The scale is so vast that the language of smash or crash barely applies. It is closer to watching the scaffolding of the universe buckle and bend. To understand why, it helps to look closely at what a filament contains. Imagine a cosmic river, galaxies flowing along its length, gas filling its interior, and dark matter forming its invisible spine. Clusters mark junction points where several filaments knot together. Between them span stretches of low-density but important material. This gas accounts for much of the universe's missing baryonic matter, thin by human standards but significant across cosmic scales. Beneath, dark matter gives these arteries their weight, shaping the motions of galaxies anchored inside. So, when one filament intersects with another, you're not just watching a set of stars being nudged aside. You're watching gravity reorganize entire rivers of matter, with galaxies swept along as if caught in a shifting tide. The first effects unfold in silence over tens of millions of years. Clusters embedded in one filament suddenly alter their orbits once they feel the tug of a second structure. Their trajectories bend, merging some groups while redirecting others. Galaxies that would once have drifted indefinitely along one highway suddenly find themselves routed onto another, a rerouting measured not in decades but over cosmic ages. The gas within colliding regions compresses, just enough to heat and glow faintly in X-rays and radio bands. Astronomers hunting for these signals know they are subtle, soft glows against the deep sky, invisible to the eye but recordable with dedicated detectors. The scale of energy is enormous, yet its light barely whispers compared to the violent brightness of supernovae. Dark matter halos drive most of the weight behind each filament. When two filaments interact, their halos don't crash and splinter like solid bodies. They drift through, only warping the fabric of space-time across the scales they cover. The evidence shows up in gravitational lensing. Background galaxies appear skewed, stretched, or split into arcs when their light passes through. When researchers stack these distortions across wide surveys, the full web's outlines appear. In places where filaments overlap or bend show up as nodes of added complexity. These nodes are the scars of cosmic restructuring, evidence that filaments do not remain still but twist, merge, and reform. Why does this matter? Because filament collisions change the large-scale connectivity linking galaxy superclusters. Imagine the web like a map of roads. Where filaments overlap, new intersections appear, rerouting the flows of gas and galaxies. Suddenly, areas that were sparsely connected see highways converging. Chance encounters between galaxies multiply, merger rates rise, and groups coalesce into denser knots. Over billions of years, this rewiring alters how superclusters grow, shifting the gravitational landscape that shapes the fate of galaxies residing inside. The consequences funnel downward into active galactic centers. Gas compressed at these filament junctions often pours inward towards supermassive black holes, feeding them at accelerated rates. When this happens, quasars flare, bright compact engines at cosmic distances churning radiation across the spectrum. To observers, a quasar lighting up might appear out of nowhere, but the underlying trigger could be as large and unseen as two filaments converging, guiding more fuel into its accretion disk. This link between filament dynamics and quasar activity has been observed statistically, reinforcing the idea that large-scale cosmic architecture directly governs the brightest single objects in the universe. Another outcome is the creation of bulk flows. As intersections redirect gravitational potentials, entire cohorts of galaxies shift, together in coherent motions spanning tens of millions of light-years. These flows are not explosions or sparks of debris, they're coordinated drifts, with galaxies moving off the smooth cosmic expansion to follow the redirected pull of newly formed nodes. Modern surveys pick up hints of such flows in redshift maps. Galaxies in certain regions appear systematically offset, drawn toward unseen mass intersections rather than continuing in perfect alignment with the Hubble expansion. The quietness of it all is deceptive. Unlike colliding stars or black holes, filament mergers don't deliver sudden fireworks. Their signals are faint, a rise in diffuse gas temperature, a strengthening of lensing arcs, a flicker of quasar brightening, or a gradual distortion in galaxy velocities. But the outcome is no less profound. Where smaller collisions end lives of stars or scatter debris, filament collisions rewrite the stage on which all those smaller dramas occur. The skeleton itself is updated, the highways rearranged, the destinations redefined. Think of it as a cosmic reset. After a collision, some strands collapse, forming thicker channels, while others stretch out to feed expanding voids. The previous layout fades as galaxies are rerouted into new gravitational basins. Civilizations inhabiting those galaxies might never notice. On human timescales, the drift is imperceptible. But over the course of billions of years, the map of the universe itself is revised. The rules of gravity do not need forceful explosions to make change. They need only time, subtle pressure, and enormous scale. Astronomers track these events because they tell us where tomorrow's galaxies will emerge. High connections mean more material cooling into clusters, lower connections mean fewer. Models suggest that filament interactions regulate star formation rates by dictating how much fresh gas arrives in galactic neighborhoods. That reshaping has direct consequences. It defines whether galaxies evolve into rich spirals glowing with blue stars or into quiet ellipticals where star formation has ended. None of this reaches us in spectacular bursts captured by the naked eye. Instead, researchers sift through weak lensing signatures, faint X-ray maps of heated plasma, and the statistical behavior of growth patterns. These are indirect, but they are enough to reconstruct the grand choreography. And surveys planned for the next decades, both ground-based and spaceborne, promise clearer pictures, maps of not only where galaxies shine, but where the invisible bones of the cosmic web shift against each other. The takeaway is straightforward. Filament collisions don't light up the sky with visible brilliance. They alter the infrastructure itself. They determine which clusters survive, which quasars flare, and where future galaxies grow. It is less a spectacle and more a reprogramming of the architecture. Filament collisions change where and how galaxies grow, not with fireworks, but by rewriting the highways galaxies travel on. And if colliding filaments are changes in the universe's structure, what happens when instead of structure there is only emptiness, vast stretches defined not by matter but by its absence? That leads to an even stranger question. What does it look like when nothing collides with nothing? When voids collide? When astronomers talk about the universe's largest structures, they don't always mean something luminous. Sometimes the biggest features are defined by what's missing. These are cosmic voids, regions of space where the density of galaxies is far below average. A supervoid can stretch hundreds of millions of light-years across, yet contain only a fraction of the galaxies found elsewhere. To study them is to look at the absence of structure, the great gaps between filaments and clusters. And just like filaments, voids also interact. When two grow near each other, they don't crash violently. Instead, they blend into a single, even larger hollow. This kind of collision is less a meeting than a merger of underdensities. There are no shock fronts, no luminous bursts. Instead, the thin walls of galaxies and gas between two voids gradually erode. Over billions of years, the scaffolding that defined their boundaries stretches and thins until the separation disappears. Seen on a cosmic map, the two empty regions become one wider basin, leaving matter further concentrated in the surrounding filaments and clusters. In other words, while galaxies smash and forge new stars, voids expand and merge by subtraction, removing structure from the web. The shape of these spaces is easier to understand when you picture the large-scale universe as foam. Galaxies and gas sheets line the surfaces of bubbles, while the interiors of bubbles are the voids themselves. When neighboring voids grow, their internal pressure from faster cosmic expansion forces the separating sheets to thin. Eventually, the walls buckle and break, and the two empty volumes unite. Rather than seeing something flare, astronomers note what is missing: filaments fading away, starfields vanishing from certain regions, leaving larger swaths of sky depleted of visible matter. For galaxies caught at those weak intersections, the story is quiet but stark. The gravitational pull of denser clusters around the voids slowly drains them away. Galaxies drift towards stronger structures, leaving the dividing zone emptier. Over time, that leads to the strangest kind of exile: galaxies cast into wider deserts with little gas to refuel star formation. Aging stars remain, but new blue giants do not appear, and the galaxies dim into isolated relics. The metaphor of a desert works here. When voids merge, the oases of activity retreat, and a more uniform emptiness spreads. Voids, of course, are never perfectly empty. Even the largest contain some galaxies and traces of hydrogen. Compared to typical regions, however, their density is severely reduced. When two of these regions combine, the dilution goes further. The sparse galaxies left behind find themselves with fewer neighbors, lower interaction rates, and reduced access to cold gas. Star-forming activity that might have once flickered runs down. While elsewhere in the cosmos collisions spark creation, here merging voids represent stagnation. Opportunities to form stars are erased not violently, but by lack of fuel. From our vantage point, recognizing such mergers requires precision. Astronomers detect voids by mapping galaxy distributions across deep surveys and identifying regions where counts drop below statistical norms. When several voids overlap, these gaps appear larger and darker. Some researchers have even linked supervoids to faint anomalies in the cosmic microwave background, like the so-called cold spot. The interpretation remains debated, but the possibility suggests large voids can leave imprints on the oldest radiation we can see. They are not invisible after all. Their size and structure echo faintly against the universe's primordial light. Why do voids merge so readily? The answer lies in expansion. Dense regions resist expansion with their gravity, binding galaxies into clusters. But emptier regions lack that resistance, so they stretch faster. Over time, small voids expand into their surroundings, and the borders between them push into one another. Unlike galaxies that need tight orbital mechanics to collide, voids have no obstacles. Their merging is almost inevitable. By the present day, surveys show that the void network is one of the most dynamic aspects of structure on the largest scales. The consequences reach out to the galaxies that hover close to void edges. As the walls fall, small galaxies find themselves stranded. Cut away from denser structures, they wander deeper into emptiness. The isolation means fewer mergers and less fresh gas to trigger starbursts. These galaxies become fossils, dim, red, and quiet. Isolated dwarfs in today's universe may be the survivors of past void consolidations, each carrying the history of a lost filament or dissolved wall. What makes void collisions remarkable is the contrast with every other kind of merger. Stars colliding yield fusion runaways and heavy elements. Galaxies colliding funnel gas into new creation. Clusters colliding produce shock fronts and radio arcs. But voids colliding do the opposite. They erase. The spectacle isn't brightness or heat, it is the removal of galaxies from certain zones, leaving nothing dramatic but instead a steadily growing silence. A single clear phrase captures this inversion: void mergers build absence. Over vast timescales, this process changes the outlines of the cosmic web itself. Filaments grow fewer, straighter, and thinner. Boundaries that once gave rich, tangled shapes to galaxy maps collapse into simpler geometries. If the universe could be fast-forwarded by tens of billions of years, the web would not only stretch but hollow, as its original meshwork collapsed into a more skeletal form. Where there were once multiple threads between clusters, only one or two remain, the rest dissolved into the growing voids. This ties directly to the universe's accelerating expansion. As dark energy drives faster growth, voids are the most responsive regions. Their interiors dilate unchecked, thinning further and pushing more galaxies to the edges. Every smaller merger accelerates. Each overlap builds a greater expanse where little remains. In the far future, only clusters linked by the strongest filaments may persist while surrounding voids expand endlessly. The fate of the cosmic web is simplification, fewer structures holding onto matter, surrounded by supervoids grown vast. Visually, a merging void would not dazzle telescopes. Observers would note instead an area with steadily falling galaxy density and faintly warmer or cooler background signals. Overlays on survey maps register boundaries fading, filaments weakly glowing before disappearing. The event is not sudden. It is charted statistically, discovered by measuring where galaxies are not found. In every way, the spectacle is understated. But understated does not mean unimportant, because the cumulative result is entire swaths of cosmic geography gone. For astronomers marking large-scale trends, void mergers reveal that the universe is not static, but evolving toward emptiness. The most massive mergers create not active giants, but larger patches of night sky stripped thin of light. Each erased filament reduces potential star formation, shifts the trajectory of surrounding galaxies, and thins the cosmic network. It's not destruction by blast, but dissolution by absence. Some studies stress that these processes influence cosmology directly. The pattern of void distribution affects measurements of expansion itself. The way voids cluster, merge, and line up alters estimates of how dark energy drives acceleration. Observing them carefully provides data not just on their shape, but on the fundamental physics of the universe. In that way, void collisions have consequences far beyond their silence. They refine our view of cosmic destiny. So, when two supervoids merge, the aftermath is not fireworks spectacle, but structural subtraction. Filaments weaken, galaxies are scattered, and gravitational scaffolding falls away. Astronomers witness not noise, but a deeper darkness. And in the long run, that is the most striking revelation. Void merging is one of the primary ways cosmic structure simplifies as time advances. With the universe's expansion speeding forward, it ensures a future where outlines fade and emptiness dominates. This carries us to an essential perspective. Colliding structures of every scale, from worlds to voids, reveal the universe not just as a builder of systems, but as a destroyer of them. From planetary impacts to collisions between galaxy clusters, the story is the same. Crashes shape the universe. These events don't just destroy, they forge the elements in our bodies, scatter metals into future planets, and restructure galaxies on every scale. We exist as the outcome of countless collisions. If this surprised you, drop a comment with which collision stunned you the most, and subscribe for more cosmic deep dives. From brown dwarfs to superclusters, astronomers now have the tools, telescopes, simulations, and gravitational wave detectors to watch these collisions unfold and read the universe's history written in their aftermath.